Students, this time we're going to take a look at the specific heat capacity of metals lab. This is one of the all-time great labs that we do in advanced topics in chemistry. In this lab, what we're going to do is test each of 3 different metal samples, all of which kind of have a silverish color. We're not going to tell you what the metals are right now, but I will tell you that one of them is aluminum, one of them is zinc, and one of them is tin. I'm not going to tell you which. All 3 metal samples have a mass of 58 grams. And all 3 of the metals have a unique specific heat capacity, which we'll be able to calculate during the course of the lab. One of the first things that we're going to do is get a beaker of water on a hot plate and turn the hot plate all the way up. Eventually, this water will get to a boil. But while we're doing that, waiting for that to happen, we're going to take a styrofoam cup and we're going to weigh it before we get it wet. So I'm going to use my handheld scale. Set the cup on the scale. And the mass is 2.54 grams. We'll record that. Then we're going to take just regular old tap water. This does not need to be deionized water. And we're going to half fill the cup. It doesn't say measure an exact amount. It just says half fill the cup. So I'm going to go over to a sink. And run the water until it's about halfway full. I'll come back to the scale, set the cup with the water on the scale, and I get 114.92 for the mass of the cup with the water inside. We'll need that number later on. Now that we've got that, we're going to take a thermometer and insert that into the water and record its initial temperature. We're done with the scale for now. Waiting for it to level off. And we get a temperature of 22 degrees Celsius. All right. Next, we're going to gently insert the 3 metals into the beaker of boiling water. And so that we don't burn ourselves, we're going to use these metal tongs to gently lower them into the beaker without getting our fingers burned in the process. All right. We're going to let the metals sit for about 5 minutes. I'll pause the video while we're letting the metals sit in boiling water. But before I pause the video, I want you to think about this question. At what temperature does water boil, at least at standard atmospheric pressure? What number of degrees Celsius does water boil at? We'll pause here. Okay, so now we've got our water boiling. Our metals have been sitting in the boiling hot water for at least 5 minutes. So it's safe to assume that they've acquired the temperature of the boiling water. Before we paused, I asked you, at what temperature does water boil at atmospheric pressure? Hopefully you know this one. It's 100 degrees Celsius. They defined the whole Celsius scale so that it would be exactly 100 degrees. So if the metals have acquired the temperature of boiling water, that means that the initial metal temperature is 100 degrees Celsius. What we're going to do is transfer one of these metals into our styrofoam cup at a time. And once we transfer the hot metal into the room temperature water, we would expect the temperature of the water to rise. But just how much it rises, well, we'll use our thermometer to measure it. Okay, so here goes. Now, at this point, the metals are very, very hot. So I definitely don't want to burn my fingers, which is why I'm going to use the metal tongs. Yeah. Let's pause for a minute. I'm going to get a better pair of tongs. Okay, now I've got a better pair of tongs to grip my metal. I'm going to start with metal type 1. It's a bit of a challenge. Okay, now I've got a better pair of tongs. I'm going to transfer metal type 1 into the styrofoam cup of room temperature water. Gently lower that in. Since the metal has now acquired the temperature of the boiling hot water, and I'm transferring it to room temperature water in the styrofoam cup, you would expect the temperature of the water and metal, the final temperature, to be higher than the water was initially. We'll record the highest temperature that this mixture achieves, the water metal mixture. And it looks like it's holding steady at 28.5 degrees Celsius. All right. The metal at this point has cooled off enough to touch. We just need that final temperature. Now, I'm going to transfer metal type 2 from the beaker of boiling water into the cup of room temperature water. And before I do that, I want to make sure that I get the initial temperature of the water. Sometimes it cools off just a bit between trials, so we want to be sure we get the most updated number. Okay, and now metal type 2. And again, the water temperature in the styrofoam cup is rising because a piece of hot metal was just transferred to it. And this time, it looks like our temperature is holding steady at about, and I'm going to stir just a little bit, 30 degrees Celsius. At this point, the metal in the styrofoam cup is cool enough to touch. Before we transfer metal type 3, once again, I'm going to get the initial temperature of the water. Sometimes there are slight variations that may indeed cool off just a smidge between trials. Okay, and now I'm going to transfer metal type 3 to the styrofoam cup. And once again, we would expect the temperature of the water inside the styrofoam cup to rise because once again, we're transferring hot metal into it. It looks like we steady out at 32.5 degrees Celsius. Okay, with that, I'm going to turn off my hot plate. We'll let that cool naturally on its own. We'll gently move this aside. And let's talk about calculations. Here's our data table. If you remember some of the numbers we had, the mass of the empty cup, 2.54 grams. When it was half filled with water, 114.92 grams. If you subtract the mass of the cup with the water in it minus the cup itself, we get 112.38 grams. All three metal samples had the same mass, 58 grams for each one. They were manufactured that way. The other thing that was inputted in the data table for us was the initial temperature of the metal. Because water boils at exactly 100 degrees Celsius, the initial temperature of all three metals was 100 degrees. Now, the initial temperature of the water, this varied. For metal sample 1, it was initially 22 degrees Celsius, and it warmed up to where it says final temperature of the water and the metal. They should have both acquired the same temperature, 28.5 degrees Celsius. For metal sample 2, the water cooled off just a smidge between the end of metal sample 1 data collection and the beginning of metal sample 2's data collection. Although I used the exact same water, it's just that it cooled off a little bit between. So if it ended at 28.5 at the end of trial 1 or metal sample 1's data collection, it cooled off to 27.5 at the beginning of metal sample 2's data collection. Metal sample 2 warmed up to 30 degrees Celsius. And then when we collected data for metal sample 3, again, there was a little bit of cooling. It went from 30 degrees Celsius down to about 29.5 degrees Celsius. When I dropped the hot metal sample 3 into the water, it warmed up to 32.5 degrees Celsius. Now we can calculate a little bit. It says delta T, or change in temperature for the metal. In every case, we're going to take 100 minus the final temperature. So for metal sample 1, 100 minus 28.5 is 71.5. For metal sample 2, 100 minus 30, that's 70 degrees Celsius. And for metal sample 3, 100 minus 32.5, uh, 67.5 degrees Celsius. Okay, for the water, final temperature minus initial temperature. And oh, and by the way, if our final temp for the metal is always lower than the initial temp, these numbers should all be negative. Okay, so the water temp, change in water temp, final minus initial. In each case, we're going to take the final temperature. So for metal sample 1, it was 28.5 minus the initial temp, 22. So that's a positive 6.5. 30 minus 27.5 is 2.5 degrees Celsius. And 32.5 minus 29.5 is 3 0.0 degrees Celsius. Okay, so that's nice data, but what do we do with it? Well, what we've got to think about in this lab is that if the law of conservation of energy holds, which is safe to assume here, whatever temperature, whatever heat energy was lost by the metal was then gained by the water. So if we can use the letter Q to represent heat energy, the Q lost by the metal equals the Q gained by the water. And of course, this assumes that you're not losing heat energy to something else. Now, one thing that's a little bit tricky is to say to yourself, all right, if I'm thinking of heat energy being lost, I'm going to put a negative sign in front. So the negative heat energy lost by the metal is equal to the heat energy gained by the water. Which also means that we can say, instead of Q, what if we say mass of the metal times the specific heat capacity of the metal times the temperature change of the metal? Because after all, students, Q equals MC delta T, right? And for the Q of the water, that would be the mass of the water times the specific heat capacity of the water times the temperature change of the water. In this lab, we were able to measure, or at least were given, the mass of the metal, the temperature change of the metal, the mass of the water we got. The specific heat capacity of the water is a known constant. It's something that is always this number exactly, 4.18 joules per grams times degrees Celsius. It's always that exact number. The temperature change of the water we measured. The one thing that we don't have is the specific heat capacity of the metal. We're going to use this rather complicated equation to solve for the specific heat capacity of the metal. And in doing that, we're going to be able to identify the metal. As in, we're going to figure out whether metal sample 1 is tin or zinc or aluminum, and whether metal sample 2 is tin or zinc or aluminum, and whether metal sample 3 is tin or zinc or aluminum. And we should be able to identify the metal based on that. Okay, so if we go for sample 1 and plug in some numbers, based on the data we collected, the mass of all the metals is 58 grams. The specific heat capacity is unknown. I'm just going to write X for that. And for our data, the temperature change of metal sample 1 was negative 71.5 degrees Celsius. For all of the samples, all 3 of the samples, the mass of the water is going to be the same because we use the same sample of water over and over again in order to do this lab, and it was 112.38 grams. Liquid water specific heat capacity is known to be 4.18 joules per grams times degrees Celsius. And then the last thing we need to refer to the data table for is the temperature change that the water experienced. And for our metal sample 1, that was 6.5 degrees Celsius. So now we've got one big equation, but it only has one variable. So we're going to solve for that. Pull out your calculators here. To get X alone, I'm going to divide both sides by 4,147. And the specific heat capacity for metal sample 1 works out to be 0.74 joules per grams times degrees Celsius. So that's metal sample 1's specific heat capacity based on our data. Let's keep going. For metal sample 2 and 3, we'll do the same calculation, but with the numbers that apply for those metal samples. The mass of all of the metal samples is 58 grams. The specific heat capacity is unknown. I'll just leave it as X. Then if we refer to our data table, for metal sample 2, the temperature change was -70 degrees. The temperature change for the water is 2.5 degrees. And just a reminder, the mass of the water is the same throughout the whole experiment. So if we plug that in, liquid water's specific heat capacity, once again, is 4.18 joules per grams times degrees Celsius. And the temperature change that the water experienced in our metal sample 2 data was 2.5 degrees. Let's pull out the calculator and see what we get. To get X alone, we'll divide both sides by 4,060. And the specific heat capacity for metal sample 2, according to our data, works out to be 0.29 joules per grams times degrees Celsius. All right, there's one more metal that we need to calculate for, and that is metal sample 3. It's going to start out the same way. All of the metals have a mass of 58 grams. Let's take a peek at the data table. For metal sample 3, the temperature change experienced by the metal was -67.5. That for the water is a +3. And once again, the mass of the water is the same throughout the experiment, 112.38. So now, once again, we have kind of a bigger equation, but there's just one variable. Let's crunch with our calculator and solve. Notice, by the way, the negative signs cancel out here. To get X alone, we'll divide both sides by 3,915. X works out to be 0.36 joules per grams times degrees Celsius. So students, those three numbers, the specific heat capacities, are really important. And for metal sample 1, once again, so metal sample 2, we worked it out to be 0.29, metal sample 3, 0.36, and metal sample 1, the number was 0.74. So if you look at the lab report, it's going to walk you through those calculations, but then the analysis says, hey, take a look at the specific heat capacities that are in the table. Can you identify which metal is which? Now, students, our numbers don't line up perfectly with any one of the three, but if I were to take a stab at it and say what's closest, I would have to say metal sample 1 at 0.74 joules per grams times degree Celsius is closest to aluminum. And I would say metal sample 2 at 0.29 joules per grams times degree Celsius, since that's our lowest calculated specific heat capacity, that's probably tin, because of the three metals, that one has the lowest of the specific heat capacities. And then zinc, the listed specific heat capacity is 0.388. Our calculated value of 0.36 is reasonably close. So I'd say metal sample 3 is probably zinc based on our data. Sources of error. Students, what do you think could cause some uncertainty in our results that was not just a mistake that we might have made? Admittedly, mistakes happen, but what's something that could have gone, not wrong, but added uncertainty? I want you can think of this on your own, but think carefully about when we transferred that hot metal out of the beaker of boiling water, fumbling as we were with the tongs. What was happening is the metal was moving through the air. Remember, it's a really hot metal. It's moving through the air on its way to a styrofoam cup of water. Any heat lost in the transfer through the air was not captured by our thermometer that was sitting in the styrofoam cup with water. So that was unaccounted for heat loss. And that could have caused our numbers to be artificially low. So if any of these are lower than what you would expect, you might attribute it to heat energy loss to the air. Maybe you can think of another one, since the lab report says describe 2. Good luck with your report. Thanks for watching.